So here at the highest level is what you can imagine cryptography is trying to do, or at least mimic. So remember Alice and Bob over their public network like the internet with an adversary present in this cloud. So imagine that they somehow built themselves a physical pipe which connected them and only them, and it was built of some impenetrable material, call it kryptonium, and nobody can look inside or penetrate that pipe. So then Alice puts her message in at one end and it comes out at the other, and this is great. This allows all the privacy and integrity goals to be achieved. So the difficulty, of course, is that we can't go around building these kinds of pipes over the internet, even if we had by any chance some kind of material with which to do it. So you can think of the goal of cryptography as being to mimic the functionality you get from that physical pipe using mathematics and algorithms. So what Alice will actually do is, rather than send her message M in the clear across the internet, she'll run a certain algorithm or piece of software called the encryption algorithm, which also operates under the influence of something called a key, an encryption key in this case, and produces an object called a ciphertext. And what's sent across the wire is this ciphertext. And what reaches Bob at the other end is also a ciphertext, perhaps the same as what Alice sent, or if the adversary is trying to violate integrity, maybe even a different ciphertext. Whatever it is, Bob puts it through a corresponding decryption algorithm, which also operates under the influence of a key called the decryption key, and gets something back. And ideally, that's the message that Alice sent, but perhaps the box will say, no, I think something went wrong and someone tried to modify this. So I'm just going to tell you that by returning a special symbol called bot. These algorithms that we use are not secrets. They're usually something that you can find anywhere on the internet. Their descriptions are public, they're embedded into standards, there are implementations out there. So all the security resides in the keys. These keys are usually short strings of hundreds to thousands of bits long, and they're chosen with some randomness in them so that they're not a priori guessable. And there are two setups. The most simple classical one is what's called the symmetric setup, where the encryption and decryption keys are the same. So Alice and Bob share a key, and that's used for both encryption and decryption. And in the public key or asymmetric setting, the encryption and decryption keys are not only different, but it's arranged that no secrecy needs to be provided for the encryption key. So the adversary in particular might know that, and nonetheless, it shouldn't be able to violate security. How these keys reach the endpoints is one problem. That's called key distribution. We'll punt on that for a fairly long time. So right now, we view the way in which keys reach the endpoints as kind of magic. And we'll study for a significant amount of time how to make use of them well to reach various goals. So what are these goals? Cryptography is concerned very centrally with that question, not only at a broad or intuitive level what these goals are, but what are they formally? How do we define them? Once we understand these goals well, we'll ask how do we design schemes, encryption and decryption algorithms that actually achieve them. And then we have an even more difficult question maybe, which is how do we know that these algorithms actually provide security? All these different questions have in some ways so many different aspects and natures, and that's an explanation of why security broadly taken involves so many different disciplines. So what we usually call computer security concerns how your computer system might protect these keys, what kind of threats there are to the system itself in the form of viruses and malware and things like that. Whereas cryptography is about the mathematics of the design of the algorithms. how do we build encryption and decryption algorithms that use their keys effectively to ensure various abstractly specified security goals. And due to the breadth of the subject, this is split up. If you're looking for computer security, broadly speaking, you have to integrate all this. But course-wise, 127 at the undergrad level and 227 at the grad level deal more with the system side, whereas 107 and 207 commensurately deal with the mathematical side, which is what we're looking at here. So cryptography is not easy in the sense that getting something that's working, that works well and gives you the security you want is challenging. And one of the reasons it's good to sort of understand that starting out is that you'll see that we're going to go through quite a bit of theory. And it's good to know that that's not for no reason. It's not just to make you jump through hoops. It's because it's not clear otherwise how to have some sort of high confidence that things work. And the simplest way to express the reason at a high level is that you're dealing with adversaries, and what adversaries do is not something we can predict in advance. We don't know what strategies they'll employ, and we have to somehow try to be secure nonetheless. Comparing this to standard software, the mechanism employed there to assess that it works well is often testing. You try some set of inputs and hope that they cover most use cases, and if that's the case, then you declare your software to be good. The difficulty with testing is that it doesn't particularly anticipate that your user is making a determined effort to make your program fail, which is what adversaries do. And so that kind of approach is not going to be too effective in cryptography. Okay, so eventually we'll start talking about all the different possible approaches and what we'll do. But let's change gears a little bit now and get a sense of what's been going on by looking at a bit of history. So cryptography is quite old. The first form it took was substitution ciphers, and these are still the most natural way to perform encryption and something we still see. If you open up a newspaper on a Sunday, you'll often find little puzzles or exercises of the form, here's an encryption scheme, break it. And it's a substitution cipher, and you're given a little bit of text and you play around with it. So what is this object? It'll enable us to exercise some of the vocabulary we've discussed already. There is a key. The key in this case is a permutation. So what's a permutation? It's a function from a domain to a range, and both the domain and the range are a finite set of letters, which is the alphabet. And the simplest cases, these are just the letters of the English alphabet, so A, B, C, D, and so on. Being a permutation means that it's uniquely reversible. So if you write out this permutation as a table, so the table will show every choice of input sigma and the corresponding choice of output pi of sigma. And being a permutation means that the second row has no repeats. You can't have, say, both A and D map to the same thing. Since A is different from D, it has to map to something. The two have to map to different things. Okay, some such permutation is your key, and it's both the encryption and the decryption key, and you should think of it as being secret and chosen maybe at random. The sender and receiver, Alice and Bob, have this key, and now we want to start encrypting. So the encryption function takes the key and the text you want to encrypt. The key appears as a subscript, so it's pi. And then let's say your text is a three-letter word, CAB, cab. And encryption is performed in this sort of natural, simple way. You apply the permutation to each letter, so you encrypt each letter separately. So you get pi of C, pi of A, pi of B. You look up the table. Those are Z and E and A respectively. And so the ciphertext sent across the wire is ZEA. To the adversary, hopefully, that looks like gibberish. Now, Bob at the other end, however, can easily recover the original message because he knows the table. Remember, the table is the key, and both Alice and Bob share it. So when he gets ZEA, he applies the decryption function, which is defined to simply take the letters seen and apply the reverse of the permutation, the inverse function, which means read the table backwards. So looking at z, he sees that above it is a c, so z, pi inverse of z is c, and so forth, and he recovers the word cab. Okay, so easy enough to perform, but then the question is, what can we say about security? And sometimes a class can spend many lectures on this or more, looking at strategies for breaking this and how you might strengthen it and many other such things. But I'm not sure how much value there is to that. These kinds of methods are not prescribed or recommended in modern cryptography. And in some ways, the takeaway lesson is just that it really doesn't work well. If you want to see why, one of the reasons is that you're encrypting each letter the same way, regardless of its semantics inside a broader text. So wherever a C comes up, it's always a Z. Knowing that, we also know that the English language has some letters having greater frequency in common text than others. For example, E is the most common letter in English text. And automatically from there, cryptanalysis starts becoming quite possible, because a good guess would be, if you have an encryption of a long paragraph, the most common ciphertext letter you see should decrypt to an E. Similarly, you might say that the next most common one decrypts to some other vowel or something, and these frequency tables can be easily found on the internet. And as you work through this and also exploit your knowledge of the language and of structure, it's surprising how quickly you can start decrypting as an adversary quite short texts. So I'll leave it at that and go on to the next historical step in the evolution, which took quite a long time. Then the first time we saw something significantly different was in the Second World War, where the Germans built something called the Enigma machine. And this was much more complex than a substitution cipher, and yet in some ways a kind of glorified substitution cipher. It would change the manner in which substitutions were done and many other things. You can see here a perhaps nicer picture. It has various things called rotors over here, and you can see that the rotors will change letters in certain ways. There were many possible choices for these rotors, and so there was a little bit of context dependence in how encryption of letters was done and so forth. And the Germans were quite confident about this, but this is one of the early lessons of cryptography, is that the confidence was relatively misplaced. There was a rather exciting and popular, well-known effort led by Alan Turing, which succeeded in breaking these ciphers and influenced the course of the war. So where do we go from there? Well, in our historical evolution, maybe the next interesting step, jumping ahead a fair amount, was when Claude Shannon decided to back up and try to look at encryption more mathematically, particularly from the point of view of trying to define what security actually is. So he looked at a system which is now called the one-time pad. It existed before his time, but his approach was just more theoretical. So in this system, the key is a randomly chosen bit string, let's say of a certain length. And with that, with this over here, I'm introducing some notation we'll see quite a bit. So on the right, 0, 1 to the power k means, just like in CSE 105, you have this set of all strings whose length is the integer k. For example, if k is 1,000, it's all 1,000 bits strings of zeros and ones, which means there are 2 to the 1,000 things in the set. Then this notation means that this particular string, k, the key, is drawn at random from that set. So it's equally likely to be any string, and that means that each bit is equally likely to be 0 or 1. Okay, so now we pick a key in that form, and magically the sender and receiver have possession of it. And now to encrypt, we assume that the message is also a string of the same length as the key. And Alice has that. And the way she encrypts is very simple. She takes the key and just bitwise XORs the message. How Bob decrypts is also then very simple. It's the same operation. If you look at the XOR operation, it's easy to see that if you take the ciphertext and XOR the key back in, you just recover the original message. Okay, but what's interesting is this extremely simple encryption mechanism somehow has a property that you could call perfect security. So Shannon gave a mathematical definition of what it meant to be perfectly secure. And effectively, it means that you get no information about the message from the ciphertext beyond what you might know ahead of time from context. And then he was able to prove that the one-time pad meets this notion. Okay, well, that's nice. And one might say, okay, why isn't that the end? So doesn't cryptography end there? We have perfect security. But there was a practical drawback to this setup, which is that perfect security is only possible when you have more key bits than message bits. So at the bottom, when I write these bars around this, here remember the message and the key are both strings of bits, and the bars denote their length. So let's say the key was 1,000 bits. Well, up here the message was also 1,000. But 1,000 is quite short for a message. I may want to encrypt files, emails, whatever, and they would be a lot longer. But this says that if the length of the message is more than the length of the key, I will not be able to encrypt with that key and achieve perfect security. This is not just true of some sort of one-time pad-like system, but for any system. So Shannon is saying there's just no way to make this happen. Okay, so that's a pretty major practical disadvantage. So it's also, however, the starting point for modern crypto, and it shifts gears in how we think about security, because Shannon's view was that security is a mathematical property. It should be impossible for an adversary to get information about your data. But if perfect security, as he defined it, is not achievable for large messages, something else has to come into play. And the insight and interesting element there is that that something is computation. And what modern crypto says is that we're no longer going to require or want that it should be mathematically impossible to get information about the data from the ciphertext. What we're instead going to say is that the amount of computation you have to put in to get such information is prohibitively large. So in principle, you could actually break the encryption. You could take the ciphertext and find out stuff about the message. But the amount of computing power you would need to do that can be made so large that for all practical purposes, it's just not possible to get this information. So now statements about security are no longer of the form "it's possible and impossible to break a scheme." They would instead be quantitative. They might say something like, suppose your attacker has 2 to the 160 cycles in some measure or so on some computer. Then there will be a certain probability with which it can break the encryption scheme. And we will say what those are. And if you look at the numbers in this example, it should be sort of fairly believable or understandable that that kind of statement is, for all practical purposes, as good as perfect security, because nobody really has that much computing time. And so that's a strong guarantee. So this shift in perspective also is a shift in disciplines, and is in some ways an explanation of why cryptography moved from mathematics, where it was born, into computer science, because now we need to draw on the computational aspects of the mathematics on which we build. So in particular, we exploit computational complexity theory to determine how we find problems that have the feature that uh, it would take a lot of computing time to find answers, and how we build on those to get security. Algorithm design tells us how we design the actual algorithms to exploit that. And these call on courses like 105 and 101, and this is why those are prerequisites for what we have here. So let me try to give an example of this notion of computational hardness that underlies all modern crypto, including, for example, TLS and so forth. So you're effectively relying on this every day, multiple times as you use the internet. So suppose someone gives you a composite number n and says, please factor it. So please find the prime factors of n. So for example, let's take 85 and say, okay, what are the prime factors of 85? So that's not hard to do. For example, I can nowadays just get on the internet and find an integer factorization calculator, type in 85 and say factor. And it says 85 is 5 times 17 and all kinds of other information. And you don't even need the internet. You can do it in your head in a few seconds. So not looking like a hard problem to do that. But that ease with which we did the computation doesn't necessarily scale well. And the real question we want to answer is, can you write a program that factors arbitrary integers? Well, you can, because we just ran one on that web page, but how would you do it? So there is a way to do that. It's quite obvious. If I have to factor a number n, for simplicity, say it's a product of two distinct primes, just like 85, I just search for divisors. So I try possible divisors starting from 2. If 2 doesn't work, try 3 and so forth. I can stop it around the square root of n, because if there's any non-trivial divisor, there's one smaller than that. N mod I equals 0 means I is a divisor. If I is a divisor, I can just return it. And since it's n is a product of two primes, the other one is n divided by I, and we would be done. So based on this, we would say, well, factoring is an easy problem for which to write a software. The difficulty is that as the size of your numbers grows, this algorithm becomes very, very slow. In cryptography, we use numbers which have hundreds to thousands of digits. So not 2 digits like 85, but imagine 400-digit numbers. And on a modern computer, it's not actually hard to work with such numbers with regard to normal operations, addition, multiplication, and so on. But factoring a 400-digit number with this algorithm will require approximately square root of the number steps. But the number 400 digits means it's of the magnitude of 10 to the power 400. So you're talking about something like 10 to the power 200 steps. And nobody has that kind of computing time. So this algorithm just doesn't cut it. Okay, so when that kind of situation occurs, algorithmic researchers or people are disappointed because they want to find fast algorithms for things, and cryptographers get excited because for them this becomes a way to develop encryption. And the idea would be that you develop it in such a way that your adversary has to factor 400-digit numbers to learn something about your data. Okay, if we are headed there, however, we'd like a little more evidence about the difficulty of factoring, say, 400-digit numbers than to merely look at the most obvious algorithm that would take 2 minutes to devise and say, oh, yeah, that one doesn't do too well. So where does that evidence come from? Well, it'd be nice to say we could prove something like there's no fast factoring algorithm, but such a proof doesn't exist. Instead, we have empirical evidence. We have many years of people having tried to find factoring algorithms, and very smart people like Gauss among them, reputedly, and they didn't find one. Actually, there are much faster algorithms, as we will see, than the one we saw, but still not fast enough to crack the numbers of cryptographic strength currently being used in reasonable time. Okay, So effectively, from our perspective, then the takeaway will be that here is an example of a problem which is computationally hard and becomes a possible basis for cryptography. But there's a couple of caveats. One is that if tomorrow someone finds a fast algorithm for factoring, it contradicts nothing. It very well could exist and it may happen. People don't believe it's going to happen, but there's no such proof. And the second is that there's a lot of excitement these days about quantum computers, and people are trying to build them, and quantum computers can factor fast. If someone builds a really effective quantum computer, all our factoring based systems would fall. And people are thinking about that, of course, in developing alternatives, but we'll get to that later. Okay, so factoring is not the only such thing. In general, we use the term atomic primitive or problem to refer to these sort of base level problems where, for some reason or the other, we see something which is computationally difficult, something that would take prohibitive amount of time for someone to do. And we need to figure out then how to turn these on their head and exploit them for security. Sometimes they're kind of natural, like factoring. It's just a mathematical problem. But others are cryptographically created. So block ciphers are things that cryptographers have built using their ingenuity and experience to have various security properties. There's no proof that they have them, but there's a good deal of understanding which says that it's likely that they do. Hash functions, as we'll see, are very similar, and there are lots of these around and in widespread use. So these atomic primitives have the feature that there's not so many of them around. We might find or devise more, but we don't really want to because it's not easy to get confidence that they really have the hardness properties we would like, particularly because their design or their discovery remains much more of an art than a science. And confidence is really just based on history and people's efforts to solve them. But also from the cryptographic perspective, the difficulty is that they don't actually, at least directly, give us encryption or give us a solution to a security problem. So look at factoring. Even if you know that given a composite number n, it's really hard to figure out the factors. What does that have to do with encryption? I have a file here and I need to encrypt it. What am I going to do? So this takes us to the next step, which is that we build higher level primitives on top of these atomic ones. And these are the problems we really want to solve: encryption, authentication, signatures, key distribution, and so forth. And there's lots and lots of these. There's a proliferation of different goals and methods to achieve them. In building these is where, in some sense, a large fraction of cryptographic work enters. And you can see this as a process of transformation. Start with an atomic primitive and then in some way turn it into a higher level one. The transform process could be sometimes very simple, sometimes more complicated. But more generally, crypto is built in this sort of Lego approach. You take little building blocks, these atomic primitives. Sometimes you use multiple primitives and you put them together and you get the end goal in which you're interested. Okay, so like I said, this particular lecture is really about broad themes, and so I'll jump around a little bit. And here's something that's central to the types of efforts we're going to make, and also quite intriguing, which is that when you design cryptography to achieve some goal, you want to start by first asking what exactly is that goal. And lack of asking and answering that question in a good way leads to schemes that are not good, often complex, unclear, and often even wrong. Yet that question is not an obvious one to ask, and historically it was some time before it was asked. Perhaps one reason is that the answer is not easy to give. So we will spend time thinking about how do you go beyond intuitive goals like, oh, from the ciphertext, I shouldn't be able to find the message, to something more mathematically and algorithmically precise with regard to what security you want to achieve. And we'll see this is subtle, but also very interesting. And this was what we will eventually devolve into strong and precise definitions of security. And I think that these goals and what we call games that we use to specify them are really a central element of what you get out of the class. Okay, so let's look at just at a high level as an example of this and to sort of indicate why it gets interesting. So we've been discussing, and probably you've heard many times through your life, about encryption and that it provides privacy, whatever is called that may mean. Somehow it protects the privacy of the data. But suppose we try to ask, well, but what exactly do you mean by it protects privacy of the data? And then you see that it's not quite so obvious. So consider an adversary that gets a ciphertext created by encrypting under a certain key a message M. So the message M is the data we're trying to protect. The encryption key is here, let's say in a symmetric setting, is a secret known to the sender and receiver. So the adversary does not know the key a priori. And it looks at the ciphertext and it's going to now start to try to break things. The question we're asking is, what is it that if the adversary does it would upset us? What is our security goal? The most obvious is if the adversary somehow finds the message. Even though it doesn't know the key and it didn't a priori know the message, once you give it the ciphertext, it does some clever stuff, some computing as well, and it finds the message. That would be bad, clearly. We all could recognize that. The more subtle thing is if I ask you, what if the adversary says, I can't actually figure out your data, but I can figure out the first bit of it. Maybe you had a 1,000-bit message, and I can figure out the first bit. And the question we are asking is, should we be upset about that? As designers of encryption schemes and users, should we view this as a threat, an attack, or should we not? And that question gets even more difficult or subtle if your adversary starts saying it can discover even more subtle things about the message. What if it says, I can't actually figure out the first bit, but I can figure out the sum, the XOR of the first and last bits? And should that upset us? Eventually, as we'll see, we do think that all of these things are problems. A good encryption scheme should not allow an adversary to do any of these things. But also, and more difficult, what other things should it not allow an adversary to do? There seems to be an endless list of such things it could do. And this is where definitions set in. A definition of privacy will allow us to, in one step or statement, using something we call a game, give an abstract condition on the adversary, an encryption scheme, that says, if you can do this, then you win. You violate privacy, and otherwise you don't. And somehow that one condition has to capture and imply security in all the senses you see here, and also many others. And as you might imagine, that's actually not obvious what this condition is. So that's, I think, one of the intriguing things we'll eventually get to. So this is one indication of why the area involves a fair amount of abstraction and mathematics. But the presence of that shouldn't lead you to think that it's not valuable in practice. Schemes that are designed via these kinds of principles, where you formally study privacy and you try to design it with a Lego approach and justify the design, are in broad use in all these protocols like TLS and others. And we will see many of them. We'll see what HMAC looks like, we'll see what OAEP looks like, and so forth. One of the things that makes cryptography attractive is how it blends many different disciplines. So within mathematics, it draws on number theory for public key cryptography, on combinatorics all across the board, on probability theory right from the start in the very definitions, and many other things as well. Historically, this may have been a little unexpected. Hardy was a famous 20th century um, mathematician, and in his book, A Mathematician's Apology, he writes something which effectively translates to saying that one of the reasons he likes number theory, in which he was a pioneer, is that it's relatively untouched and it's kind of kept away from the sordid affairs of people. It doesn't have any uses. He would be perhaps surprised now when number theory is the basis of modern systems like RSA, and you're using number theory every day and every time you make a TLS connection. So where are we today in this quest for security? We've developed, or we'll see how we will develop quite a bit of crypto, and there's many other things, but it's fairly evident if you look around that security is much of a concern. Server breaches are common, malware infiltrating computers are common. We see loss of information and private data and credit card fraud arising from break-ins to servers. Those are fairly visible. Perhaps what is less obvious is the way our privacy is compromised by the harvesting and collection of data about us. Every time you go to a website, they're collecting information about you. Every time you communicate through Gmail, Google is, connecting information about what you're sending. Various national security agencies have mass surveillance operations. So it's worthwhile to be informed about these things and somehow recognize the importance of privacy in our lives and how it's being compromised. Cryptography is one of the tools or mechanisms we have against this kind of privacy loss, but it's not the only one, and by itself it won't suffice. We've focused so far mostly on these problems of getting privacy and integrity, but modern crypto goes well beyond that. It has mechanisms for things like computing on encrypted data. You can leave your data encrypted and nonetheless perform a computation on it in such a way that only the answer of the computation comes out. You can create databases where information is kept encrypted, but you can nonetheless search on it. You can enable different communicating parties to compute joint private functions of their inputs. So for example, you want to run a machine learning algorithm to develop a model on medical data that's held across multiple hospitals, and these hospitals don't want to share their data. And we can provide algorithms whereby the privacy of the data is preserved, but nonetheless some machine learning model is eventually created. And all these exciting things are getting more and more practical as we go along. So what it would be worthwhile for you to get out of a class like this, at the very least, is the ability to think in terms of security. Sometimes that's called a security mindset. It means that you can look at situations, software, and usage and applications in a different way in which you identify threats. You can look at solutions and evaluate their security merits. You can design your own security solutions and you can develop tools that people can use. And at the very least, I often say that something, if you come out of the course with, is valuable even beyond other things, is what I'd call a sense of paranoia. Just this understanding that everything you look at can, under adversarial situations, fail. And you can see how. So let's turn to a little bit more about the class itself. Historically, 107 has been viewed as a challenging class, in particular because it's theoretical. So it demands expertise in mathematics and theory. And the types of students who do well, I'd say, are ones who are genuinely interested in the material. They're not here just to get grades, but they develop an actual interest in security and cryptography and mathematics and things like that. And challenges maybe stir them more than deter them. It's worthwhile to understand everything. But what I mean by that is that not to just try to understand what you think is relevant to solve some problem on the homework, but everything, because in the end, you kind of don't know exactly what's relevant. But if you understand everything, you can do it quite easily. Another characteristic of successful students is that they tend to talk more and have questions more about the actual material than of the form, how do I do this homework? Yet another characteristic is that although we will see many examples, there's an understanding that examples are only illustrative and one has to understand the theory behind them. Ambition is a route to success. People who enter the class saying, I just want to pass and graduate, risk not passing because they perform at somehow minimal level. But those that enter saying, I'm going to get an A, well, they often do actually. So it's recommended when you look at the materials to consider that there are two ways of doing this. One is what I call random access mode. What that means is that you start from an assessment. Here's the homework, here's the quiz problem. Now let me go back through the copies of the slides or go look at the lecture and see what do I need to solve this. This is not going to work well. What works better is if you first go through the material, the slides, the lecture, make sure you understand it, and then attempt your homeworks and quizzes. And you might find when you do that they become quite easy. One reason for this is that it's not always evident what exactly you need to solve a problem. It's somehow something global. Sometimes I've seen students who want a kind of recipe for success. They say, tell me what to do. I'm willing to work, but I want to know how to succeed. But I don't really have such a recipe because things like that are very subjective. Different people see things in different ways. And part of the interest and challenge is to find your own path to success. Okay. And